In mega engineering, extreme height is not a trophy, it is a liability. At 335 meters, the Rogun Dam in Tajikistan stands taller than the Eiffel Tower, but this record-breaking stature effectively creates a vertical kill zone. The Vaksh River hammers against the structure with relentless hydraulic force, turning the reservoir into a massive potential energy weapon. The danger is not just the water, it is the container. This colossus sits directly on a tectonic fault line, requiring a design that functions less like a wall and more like a flexible spine. Every cubic meter of water adds pressure to a structure that must survive earthquakes capable of leveling cities. The critical question echoes through the control room. Will the seam hold? Seismic monitors confirm that the bedrock beneath the foundation is in a state of perpetual microscopic shift. If the surface terrifies with sheer altitude, the underground kills with confinement. Up above, the focus is vertical, layers of earth rising to 335 meters, monitored by geotechnical sensors for the crushing hydrostatic pressure to come. But deep beneath the crust, the enemy is the rock itself. Engineers are carving out machine halls vast enough to swallow a Gothic cathedral. This is not just excavation, it is surgery inside a vice. The mountain exerts millions of tons of tectonic stress, constantly pushing inward, trying to snap these hollows shut like a geode. The logistics here defy standard engineering. The transport tunnels are barely wider than the cargo they carry. A steel turbine runner, weighing as much as a fully loaded jumbo jet, inches forward on a hydraulic transporter. The air is thick with the smell of diesel and the deafening echo of ventilation fans. The clearance between the steel payload and the raw rock wall is less than the length of a human hand. One wrong steering input scrapes the payload against the mountain. The convoy crawls forward, dragging the station's heart toward the installation pit. But the static loads of the underground hull are nothing compared to the kinetic energy of water, capable of cutting concrete. Engineers clear the initial path with standard drill and blast tactics, securing the roof with steel ribs. But raw stone would dissolve under the friction. When the diversion tunnels activate, water rushes through at torrential velocities. The walls vibrate with a low-frequency hum that rattles the teeth. Inside the flow, physics turns hostile. Pressure drops create vacuum bubbles that implode against the stone. Cavitation. These microscopic shockwaves act like millions of chisels, pitting the surface and eating the tunnel from the inside out. To survive this bombardment, crews install a secondary lining. They use a hyperdense concrete mix reinforced with silica fume and steel fibers to resist the abrasion. It creates an armored skin. Behind this shell, high-pressure pumps inject cement grout into the mountain itself. The liquid fills every hairline fracture, bonding the lining to the rock face and turning the fracture geology into a monolith. The trap is set. The deep rumble fades into silence. Where blasting is dangerous, mechanical worms take over. These are not simple drills, they are autonomous subterranean factories. The tunnel boring machine features a cutting face with a diameter exceeding 14 meters. That is the height of a 5-story building, grinding through the earth. To prevent the tunnel from collapsing, the machine pumps a pressurized bentonite slurry against the rock face. It turns the excavated soil into a thick, abrasive soup. A surface plant filters this mixture, separating the solid rock from the liquid, which is pumped back down in a continuous closed loop. Zero waste. Inside the shield, robotic arms place precast concrete segments to seal the tunnel instantly. But the true engineering marvel happens at the end of the line. The machine does not stop. In a specially excavated cavern, hydraulic jacks shove the thousands of tons of steel across greased skids. A 180-degree U-turn underground. The beast realigns to dig the parallel return tube. The cutter head exerts 4,000 tons of thrust against the wall. However, this excavated rock must go somewhere, creating a logistical nightmare that relies entirely on rubber and diesel. Once the subterranean drilling concludes, the engineering battle moves to the surface, where the enemy is simple friction. A haul truck the size of a 2-story house grinds up the quarry ramp. The ground vibrates. You feel the approach of 300 tons before you see it. This is not driving, it is the management of extreme forces. The diesel engine screams, but it does not turn the wheels directly. It acts as a generator for massive electric motors in the hubs, providing enough torque to climb a grade that would stall a tank. The weak link in this chain is rubber. One sharp rock or a single aggressive turn generates fatal heat inside the compound. A tire blows out with the force of a grenade. The cost to replace just one is 40,000 euros, the price of a brand new luxury car, erased by a moment of friction. Without this calculated abuse of machinery, moving the earth required for a mega dam would take centuries instead of years. But moving millions of tons of rock is only half the battle. Sometimes that rock must be transformed into a shield against total catastrophe. February 2017, the Oroville Dam. A roar louder than a jet engine shakes the bedrock as the main spillway begins to disintegrate under the force of extreme meltwater. The concrete fractures, the hillside dissolves. 188,000 people downstream are ordered to flee immediately. The water recedes, but the clock starts ticking. Engineers face a terrified deadline. They have 5 months before the next rainy season to rebuild 900 meters of the chute. It is not construction, it is emergency surgery on an open artery. The lower ramp presents a punishing 4-to-1 slope. Standard pavers would slide into the abyss. Crews deploy specialized roller-compacted concrete, winched down the steep incline to achieve a surface smooth enough to handle the violence of crashing water. In Colorado, the Gross Dam project takes this material science vertical. To raise the structure by 33 meters, builders do not simply pour wet cement, they laminate the dam. Bulldozers equipped with GPS guidance spread dry concrete in layers of just 30 centimeters. Precision is absolute. If the bond fails, the dam fails. They climb at a rate of 30 centimeters per vertical day, fusing the new mass to the old base until it becomes a single monolithic block. The heavy machinery finally stops. The concrete cures in the cold mountain air. The valley holds its breath for the first drop of rain. If dams hold back water, here engineers decided to walk right through it. The Fehmarn Belt project abandons the traditional drill to solve a different problem, crossing 18 kilometers of the Baltic Sea. You do not dig this tunnel, you sink it. On the coast, a purpose-built factory operates like a shipyard for static giants. It churns out the tunnel spine, 89 hollow concrete elements. Each segment is 217 meters long. The weight is staggering, 73,000 tons, equivalent to a fully loaded aircraft carrier. Then, physics plays a trick. The dry dock floods with seawater. The concrete monster lifts off the floor. It floats. Tugs drag the segment out to the open ocean, maneuvering it over a trench dredged in the seabed. This is not construction. It is a nautical operation. Ballast tanks flood and the buoyancy vanishes. The element begins a controlled fall into the cold, dark water. Sensors track the descent. The margin for error is almost non-existent. 12 millimeters. That is the precision required to dock a structure the size of a skyscraper at the bottom of the sea. Once the steel bulkheads touch, the ocean takes over. The weight of the Baltic Sea compresses the massive rubber Gina gaskets. The external pressure crushes the joints together, creating a seal stronger than the concrete itself. Inside the joint, powerful pumps scream to life, evacuating the trapped water to create a vacuum that locks the tunnel for good. Rising from the crushing depths of the sea, we face a new enemy above the surface: gravity and wind. The construction of the Zuari Bridge in India is not merely a building process. It is the tuning of a titanic instrument. The engineers employ the balanced cantilever method. The road extends outward over the water, segment by massive segment, with nothing underneath to hold it up. It is a high-stakes balancing act. To keep the structure from snapping under its own weight, the load must be transferred instantly to the pylons. The solution lies inside sleek, high-density polyethylene ducts. Bundles of galvanized steel strands are threaded through anchor boxes with millimetric precision. To the naked eye, they look like slender lines against the sky. In physics, these thin cables are the only thing preventing thousands of tons of concrete from plunging into the river. Hydraulic jacks grip the steel and apply calculated force. They pull the bridge into its final geometry, but tension creates a new risk: resonance. To stop the wind from vibrating the cables to the breaking point, engineers install dampers that absorb the kinetic energy of storms. The finished bridge is never truly still, constantly vibrating and flexing as a living, dynamic system. From the logistics of catastrophe, we shift to the critical resuscitation of doomed structures. The city of Valencia Stadium was built in 1968, a concrete bowl designed for cheering crowds, not heavy industrial lifting. To modernize it, engineers needed to suspend a roof over 17,000 square meters. But the existing skeleton was already at its limit. Adding standard weight would crumble the 50-year-old columns like dry chalk. The solution required bypassing the building entirely. Engineers designed a structural parasite that holds itself up. The geometry is a bicycle wheel turned on its side. A massive compression ring weighing 1,040 tons is assembled around the perimeter. That is the equivalent of 2 fully loaded Airbus Super Jumbos hovering over the stands. This steel halo does not crush the old concrete, it squeezes inward. Inside the ring, high-strength cables are strung like spokes. Hydraulic jacks pull the steel tendons taut. The metal groans as the tension climbs to thousands of pounds per square inch. The outer ring resists the pull, locking the system into a state of self-contained equilibrium. The contrast is violent. Below, the weathered, rough-textured cement of the 60s remains fragile and static. Above, a slick, high-tech membrane floats in the air, held in place by invisible forces. The roof does not rest on the stadium, it levitates above it. The structure stays aloft not because it is rigid, but because every cable is pulling against another in a permanent state of war called tensegrity. From the static rescue of a stadium, we move to the dynamic surgery of the world's main artery. 12% of global trade passes through the Suez Canal, but the desert constantly fights back. Silt and sand accumulate on the seabed, threatening to ground the largest vessels on Earth. The countermeasure is the Almira, a massive cutter suction dredger. Mobilizing this equipment requires military precision. The loading window onto a heavy transport vessel is absolute. 2 hours, 120 minutes. Amidst the guttural roar of heavy diesel engines, the transport ship submerges just enough to let the dredger float over its deck. A single miscalculation in draft or stability, and the channel remains blocked. This war against entropy extends to the underground veins of cities like Denver, where robotic sensors now hunt for corrosion in lead pipes before they burst. Global infrastructure relies on this invisible, constant friction against decay. When the system works, it produces the only metric that matters: silence. At sea level, the problem is sand, but at 4,500 meters, the enemy is the atmosphere itself. Oxygen here is scarce. Heavy machinery designed for the coast begins to suffocate in the thin air. Inside the combustion chamber, fuel fails to burn completely. Thick plumes of black smoke bellow from the exhaust. The engines operate in a state of chronic anemia. The loss is physical and immediate. A massive bulldozer loses 40% of its power. To compensate, engineers must recalibrate injection systems, forcing machines to work harder just to achieve basic movement. But the geology is as hostile as the air. Building a road on a vertical cliff requires surgical precision, not just dynamite. The technique is called pre-splitting. Rows of drill holes are loaded with exact gram weights of explosives. They detonate milliseconds before the main charge. A clean, controlled fracture runs through the stone. This artificial crack acts as a shield, stopping the shockwave from shattering the mountain face. When the dust settles, the machines retreat. Men suspend themselves on ropes over a 500-meter abyss. Below their boots is a void deep enough to swallow a skyscraper. They are stitching the Andes together. Steel anchors 9 meters long are inserted into the drilled shafts. A pneumatic hammer drives the final bolt into the unstable rock, locking the cliff against gravity. From the freezing heights of the Andes, the engineering war shifts to the scorching sands of the Sahara. The enemy here is not thin air, but the sun itself. Egypt is constructing the New Delta Project, an artificial river stretching 114 kilometers through the desert. That is longer than the Panama Canal, built in a place where liquid should not exist. The challenge is brutal. How do you transport fresh water through plus 50 degrees Celsius without it evaporating into the sky? The answer lies in sealing the earth. Engineers line the entire channel with high-density polyethylene, or HDPE. Concrete slabs lock this chemical armor in place, creating a completely impermeable skin between the water and the thirsty silica. Gravity assists the flow through a laser-precise slope of 1 inch for every 100 feet. It is a delicate balance. 9 billion euros. That is the price of turning dust into arable soil. The El Hammam station drives the flow, defying the arid climate to ensure food security. Humanity conquers the drought by keeping billions of cubic meters of water in constant motion. These projects prove a single undeniable fact. An engineer is not a builder, but a warrior. We began with a skyscraper hovering over a city, defying gravity with a hidden fix. We threaded massive pipes beneath Denver and hauled a 3,000-ton dredger across dry land. We climbed to the freezing heights of the Andes to shatter rock, and finished here, fighting evaporation in the Sahara. City, mountains, desert. Nature resists every step of the way. It attacks with wind, with altitude, and with scorching heat. But human ingenuity pushes back. We forge steel to hold up the sky and dig canals to bring life to the dust. The map is rewritten. The limits are pushed. We have solved the puzzles of the past. But as the world changes, one question echoes in the silence. What will be the next impossible thing we build?